Let's see.
I was blocking the kick and I blocked like this instead of blocking.
All right. I think it's time for me to start. Let me. Well, not quite, but now it's time. I will begin with a word of prayer. Dear Father, we thank you for this day, and I thank you for this class. Just ask you to be with us, help us to glorify you in what we do, and just understand a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. So momentum. What's momentum? So here's the definition. Given mass m with velocity v, the momentum p is a vector, and it's simply defined to be mass times velocity. So the momentum is a vector. It's the mass times the velocity. And so, like, force has units of what? Newtons. Velocity, meters per second, right? I mean, acceleration, meters per second squared. Momentum, what's the units for momentum? Yeah, a kilogram meter per second. So it's unlike force. We don't have some kind of special unit named just for it or anything. So we just have to use composite unit, kilogram meters per second. And so the first thing to ask is, well, what does this do for us? Well, a variety of different things. Let's look at Newton's second law for the single mass, right? What's that? So you guys remember the net force, right, is equal to the mass times the acceleration. My m seems to have gone from uppercase to lowercase. Fine, I'll unuppercase it. There we go. Sorry about that. It doesn't matter, just pick one. And all right, so that is what? That's m times dv dt, right? And so long as the mass is constant over the motion, right? If we consider the constant mass case, this is equal to ddt of m times v, right? So for constant mass. Right? And, well, what is that? This is momentum, right? So what we find then is that the net force is equal to, in fact, dp dt. And so this right here actually turns out to, in some sense, be more foundational than F equals to ma. Because it turns out that F equals to dp dt is the right approach to take to write down equations of motion if the mass happens to be variable. So I derived this formula in the constant mass case, but we'll see that this allows us to solve problems where the mass might be varying with time. If it doesn't vary with time, though, it's just another way to look at things we already know, right? For example, we could rewrite kinetic energy in terms of momentum. What's the kinetic energy for a single mass? It's what? Kinetic energy is 1/2 mv squared, right? But you could also write that as 1/2 m v dot v, right? V squared is the dot product of velocity itself. So v is p over m, right? So I have 1/2 m momentum divided by mass, dotted with momentum divided by mass. The m's, they be canceling, and we get ourselves a p dot p divided by 2m, or as we would more commonly write it, p squared divided by 2m. So there you go. The kinetic energy in terms of momentum is equal to the momentum squared divided by twice the mass. That's the formula for kinetic energy in terms of the magnitude of the momentum. So there's that. Another important concept to talk about is change in momentum. So how would we calculate the change in momentum over some interval of time? This is what's known as impulse. Impulse. A change in momentum. All right. So delta p, we do integral from t1 to t2, right? Integral from t1 to t2 of dp dt, right? That would be the net change theorem. If we integrate the rate of change, the infinitesimal rate of change, that gives us the net change, right? So that's just calculus, right? That's just calculus. But since we just had this discussion, if we know the net force, and we're talking about a single mass here, then we can say more, right? This is also the integral, say from t1 to t2, of the net force integrated over time, right? That would calculate the impulse here, if we could integrate the net force. In other words, and okay, so in a special case, right? If the force was constant, we can simplify this further, right? If F net is constant over the duration, then this formula above simply becomes the change in momentum is to that constant force, whatever it is, times delta t, right? We have this. So that, again, just for a constant force. If the force is variable, then we'd have to actually do the integral. But there you go. And this leads us to some, simple concepts like we can talk about average force, right? What's the average force? So, definition, the average force, we would just calculate from like the change in momentum over the change in time. This would give us an average force, right? Of course, before we could have calculated average force by what, like mass times change in velocity over change in time in our previous way of thinking, right? But now we can calculate the average force by change in momentum over change in time. Let's look at an example. Some cats will be hurt in this example. All right, so example 1. You have a brick wall. Very, so a noble father, yes, takes a cat, and I'll draw the cat as such. And then that cat gets thrown into the wall with velocity v naught, right? And then the cat bounces off the wall like that with velocity vf. I think there's more information here, though. This evil cat. Oh, yeah, I've got some angles involved. So he throws it horizontally. So v naught's pictured correctly. But I say he bounces off the wall with speed of so he's 10 meters per second is the incoming speed, horizontal. The outgoing, after he bounces off, he's 20 meters per second. Whoa, how's that go? I guess the cat must have like sprung off the wall, I guess. That's what not as exciting as I was hoping. It seems like the cat survived. So the cat springs off the wall at 20 meters per second, right? And I also tell you that, put it over here so I got room for my picture. I also have that it goes off 20 meters per second, angle 30 degrees above the horizontal. So the cat comes in here, hits the wall, and then comes back out like this with Vf of 20 meters per second. Right, and the angle here is 20 degrees, I think I said. All right. Did I say 30? Oh, 30. Yeah, 30. 30 degrees is more fun to calculate. I mean, whatever. But so there's the deal. There's the velocity before. There's the velocity after. And the mass of the cat, it's a 5 kilogram mass of the cat. 5 kilogram evil cat. So the question then is, what's the average force of the wall on the cat? So that's the question. Find average force of wall on cat, right? So we can calculate this by calculating the change in momentum over the change. I also told us how much time it took in the problem, which I've forgotten to write down. I said this all takes a process. 0.1 seconds is this whole process. The rebounding takes a delta t of 0.1 second. All right. Okay, so, you know, this really should not be here. Anyway. So, the average force is delta P over delta T. All right, so we need to figure out what the delta P is. So first of all, let me do it up here, I suppose. So you guys tell me, this is the easy part. What's P0? What's the initial momentum? It's that one. No trigonometry required there, right? It's horizontal. P0 is what? I heard of 50 kilogram meters per second. 0, right? Yeah, gravity's got nothing to do with it. So P0. So yeah, I mean, now if we're talking about a process over a finite time, where gravity has enough time to work, then yes, gravity could not be ignored. Because gravity does work on the object, and it changes the momentum. Yes, very much so. And we'll see that in a future example, just not this one. See, basically the way to think of it is this happens so quickly that gravity doesn't have any time to do anything here. And I'm saying 10 meters per second. I drew it over here, but what I mean by that is it's 10 meters per second right before it hits the wall. And I drew this over here like that. What I really mean is it's 20 meters per second right after it rebounds off the wall. There's not been enough time for gravity to take away the vertical component to the velocity and reduce the momentum in the negative vertical sense. Uh-oh. I seem to have developed a cough. So 50 kilogram meters per second, 0. And PF, well, MVF, right? So 5 kilograms. All right, if that's, so I've got minus the cosine of 30 degrees times 20 meters per second. See why the minus? Because the velocity is going that way afterwards, right? And on the other hand, sine of 30 degrees times 20 meters per second for my vertical component. So if we work that out, what do we get? Minus 86.6 and 50, I think. All right, so we got that. Now we can calculate the average force. What we do is we do the final momentum minus the initial momentum here, divided by my delta t, which is, 0.1 seconds. So subtract, right? We get what? We get minus, 136.6 kilogram meters per second, and then minus 50. Is that right? Oh. 50. kilogram meters per second, all divided by 0.1 seconds. So my average force apparently is listen to me, 1366 minus 1366, and then 500, and the units on this guy is newtons, right? That's the average force. So what's the magnitude? What's the standard angle? Let's find the magnitude and standard angle of that force, right? So the magnitude of the average force is what?
1366 squared
Uh-huh.
plus 500 squared, all squared.
That is true. So that works out to, of course, that's got units of newtons. And when you crunch the numbers, that works out to 1455 newtons. So there's your magnitude of the average force. What's the standard angle? Inverse tangent of, what do you say? 500? 500 over minus 1366? Now, inverse tangent, right? So let's draw a picture. The average force here, it's in this quadrant over here, right? Because we've got a negative x component and a positive y component, right? So as a picture, it's like this. We should be finding an angle between 90 and 180, right? That's in quadrant 2. But that's somewhere between 0 and minus 90, right? So I heard somebody say add 180. I think that would be correct. That's what we got to do, right? So plus 180. And so that gives me 159.9 degrees. So I know some of you are thinking about, how can I survive this course, right? Like, how am I going to make it past this horrible course, right? And one of the simple things you can do is learn how to do this correctly 100% of the time. Many of you lost many points on this on test 1, needlessly. That doesn't have to happen on the final, right? So learn to be very careful about finding magnitude and standard angle. That's, oftentimes 10% of the final right there, Yeah.
How can you find the tangent angle with three-dimensional planes, like x, y, z?
Well, we wouldn't. There is no standard angle for x, y, z. There we have to talk about the direction in terms of a unit vector. Or if you're in a different context, you could talk about the direction cosines. You could talk about like alpha, beta, gamma, the angles measured off the coordinate axes. Some people would do that, but I haven't done that in here. Yeah. So in short, the answer is I can't. In 3 dimensions, one angle doesn't do it. It's not enough information. So. Okay, so how about one-dimensionally? What goes on? So I've showed you some 3-dimensional stuff. That was a 3-dimensional example. Notice that this integration, if we think about it in the one-dimensional context, we can do calculus 1 for the one-dimensional context, right? We don't need vectors, but we do need working knowledge of calculus 1. And so what happens in the one-dimensional context here? Can you, what happens here for this formula? By the way, sometimes people use a J for impulse. You'll see this. Sometimes people use like a J for impulse. I have no earthly idea why, but you'll see this notation, J for impulse. Yeah. All right, so if we're one-dimensional, the impulse, we could drop the vector and just say J, right? So one-dimensional context. We could just write J, change in P, integral from T1 to T2, and, dp dt, there's just one component. And of course, that is still going to be the net force, right? But now we're not integrating a vector, we're just integrating a scalar like that. And as such, we can think about it graphically, right? So like, for example 2, if I have time goes this way, right, and the force goes that way, and I give you guys a graph, something like this, you know, wee, doo-doo-doo, 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 like that, let's say, and I'll put some numbers here. Suppose that's 2 seconds. Make that 3 seconds, actually. We'll make this over here 2 seconds. I'm going to make this level it gets to, say, 10 newtons for the sake of discussion. And we'll make this over here 4 seconds, all right? Then we can ask, you know, what is the, if this is the force time force graph, right? What is the impulse delivered to the system over various intervals, right? Like A, we can find impulse over, say, time 0 less than t less than, oh, I don't know, 2 seconds. All right? That was supposed to be impulse. I tried. So B, find impulse, oh no, over, let's say, 2 seconds, less than or equal to t, less than or equal to 3 seconds. And then part C, I'll say find the impulse over, let's say, 3 seconds to 4 seconds. Yep. Yes, exactly. So we don't need to find the formula for f as a function of time, right? We can go back to basic calculus 1 and say the integral is the signed area under the curve. Very good. So what's the area of a triangle, right? So
Base times height.
yeah, 1/2 base times height. So the height is 10 newtons, the base is 2, so we've got what? 2 times 10 is what? 20 divided by 2, we get 10. The change in momentum here for this case would be, oh goodness, 10 kilogram meters per second, right? Do you guys see that? So what I'm doing is the area of the triangle, 1/2 base times the height. So the base is 2 seconds, the height is 10 newtons, so I get 20 newton seconds. And then I have to divide by 2 because it's a triangle. So 10 newton seconds. A newton second is also a kilogram meter per second, all right? The seconds, they be canceling. And so this piece right here, that's even easier. What's this area? Yeah, we got 10 times, so 1 second is the change in t, right? So 10, yeah, so 10 newtons times 1. So the change in momentum there, let me call this the change in momentum for part A, the change in momentum for part B. Oh, it's the same, isn't it? 10 kilogram meters per second. All right, great. And, oh, I guess this one, let's make it exciting and different. This looks like maybe a -8 newtons. Ooh. All right, so if that's -8, what's the area here from 3 to 4? -8, yeah. Change in momentum in case C would be -8 kilogram meters per second. I probably should have arranged this so that we didn't always have like 1 second. Or well, this one had 2 seconds, I suppose. But anyway, you guys know how to calculate areas under graph, I assume. But so anyway, if I have a question like this on the next test, it shouldn't be hard to get it, right? Yeah. Okay, so what's the net? If we think about all together from time 0 to time 4, what's the change in momentum over the whole time period? yeah, I got a 10 plus 10 minus 8. So I heard a, what'd you just say? 12 kilogram meters per second. All right. And what's the average force over this same time period? Change in T over the change in T, right? Which is 12 kilogram meters per second divided by, change in T was 4 seconds. All right. So yeah, we get 3 newtons would be the average force for my silly example here. There's an equally silly example in the notes for you guys to chew on. All right? Yeah. So let us move along. Hypothetical question. If I doubled the speed, oh no, sorry, let me just a second here. I gotta get my question stated properly. Suppose you got a mass, right? And you double its velocity. How would you compare the momentum before and after? If we double the velocity, we've done what? We've doubled the momentum, right? Because momentum is just mass times velocity. So if I double the velocity, I've doubled the momentum. How about kinetic energy? If I double the velocity, what have I done to the kinetic energy if the mass stays the same? What's that? Did you say quadruple?
Yes.
Okay, that would be correct. Yeah. Very good. So here is an example where we have variable mass. All right. So this is a kind of a silly example, but I think it illustrates the new ideas here. So what I say is you have a street cleaner, and it turns out as it picks up junk, its mass changes according to its initial mass plus alpha t, just for the sake of looking at something with variable mass here. I say if the motor creates a constant force F naught, then we can derive the resulting acceleration by Newton's second law in momentum form. So suppose motor gives constant force F naught. Find motion. All right. So this is a problem we couldn't have solved before, because before we had, at our base assumption was that mass was constant. I don't know if you noticed this or not, but we never let mass change in all of the problems that we worked, right? Like the mass was what it was, and we tracked it, and whatever happened, happened. But now we can think about variable mass because we have Newton's second law in momentum form, which looks like this. The net force, which in this case is F naught, is equal to dB dt. Now we're focusing our attention, guys, on the horizontal motion, all right? And I'm neglecting, admittedly, I'm neglecting friction or anything like that. We're just going to completely focus on the force of the motor and the resulting motion that comes from thinking about the mass being variable, all right? So, excuse me. P is what? mv, right? But this, now we've got two terms. We've got dm dt times v plus m times dv dt, right? Because the mass is changing. But I've told you how the mass changes. I made this problem relatively easy to think through. So dm dt is what? It's just this particular constant, which is descriptive of like how quickly the street cleaner's picking up trash. So alpha v, all right? And then we've got plus m, which by the way is m naught plus alpha t, times dv dt. All right? So, can we solve this problem? I think so. Let me rewrite this. So we've got m naught plus alpha t times dv dt is equal to f naught minus alpha v, I believe. Right? So I'm trying to isolate the velocity. So I think we can solve this by like, oh man. So I'm kind of low energy today. Yeah, okay, so we can separate variables. Let me do that. So we've got dv over f naught minus alpha v equals to f naught dt divided by m naught plus alpha t. Remember when Calc 2 was just about integration? Do you remember those days? Very nostalgic, isn't it? So, hey, this isn't a sequence, is it? So look on the bright side of things, right? We're back to the easy part of Calc 2, when you're just integrating things. Yay! I heard some story about there being sequences now. So, so I just separated. Now I can integrate. This is minus 1 over alpha natural log the absolute value of f naught minus alpha v equal to, you know, f naught over alpha natural log the absolute value of m naught plus alpha t plus a constant.
Before you integrated,
Uh-oh.
how did you get there? Did you divide?
I'm a little, I don't know how I got f naught in both places. That doesn't seem right.
Can you show your in-between step?
I thought it would just be m0 plus alpha t over.
Yeah, I think the solution is simple enough, which is to devote this to destruction. There we go. I'll get biblical on it. There we go. There we go. Yeah, I somehow created an f naught from nothing. It's a spontaneous creation. We all know that's unphysical. I heard a really interesting podcast recently on the difference between natural and supernatural. I don't know if I can find a good format to share it with you guys, but it's really, really interesting. See if I can find it. So that's plus a constant. And then we can, you know, do algebra. And if you don't mind, I'm going to skip past the algebra and just show you what happens. I'll guess maybe I shouldn't. I've got alpha on both sides, so I can just multiply by alpha. And this will get me to, you know, well, I tell you what, I'm tired of the math here. I'm just going to go ahead. So what I have done, not optimally, guys, is I forgot to integrate from like time 0 to time t. So anyway, there are a little bit more details in the notes, but I think I should go on and not let this linger too long. This example, v naught minus f naught over alpha. So there you go. That's the velocity. So what happens here as time goes to infinity? If you could imagine a street sweeper sweeping garbage up over infinite time, that sort of thing would even make sense. But yeah, this piece gets smaller. Like this piece gets larger and larger. So this piece gets smaller and smaller. And yeah, the terminal velocity for this problem is just f naught over alpha. Yeah. So, yeah. And for small times, what happens when t is about 0? What do you got? Let's see if that makes sense. Let's check that. T equals to 0. What do we got? V equals to what? F naught over alpha plus m naught v naught over m naught minus f naught over alpha, also known as v naught. That's good. So the initial velocity ought to work out to v naught. That's the meaning of v sub naught. So yeah. All right, let me see if I can extract a little bit more wisdom from this example. If you were to look at this in terms of like mass times acceleration, we could do that. Check this out. So if I go m times dv dt, right? M times dv dt, which is this term right here, right? It's equal to f naught minus dm dt times v. In other words, it's f naught minus alpha v. So it's as if, one way of looking at this is you have F equals ma, but the force is varying according to the velocity with this alpha v. I mean, there's just like, there's this additional force here to think about. That's another way of thinking about these kinds of problems, which I don't particularly care for. I prefer to think about it as dp dt and to just kind of work out from there. But okay, so anyway, another example you might think about is like, the place where this matters and perhaps is more interesting is we could think about rocket motion, right? A rocket's a variable mass problem where, you know, the thrust, you have more or less a fixed thrust from some engine, right? And as you're going up, you're losing mass because you're shooting mass out in order to go up. So the amount of mass that you're accelerating is decreasing, and you know that whole interplay between losing mass and gaining speed and all that, it all has to be worked out with calculus, and you can't use F equals to ma in that problem. You really have to properly use F equals to dp dt because the mass is changing. So the silly Ron-Swanson problem I gave earlier in this class is a little bit farcical because I was assuming that whatever, you know, thrust was coming from rocket boots or something, it was such that it wasn't changing the overall mass, right? So we could ignore the problem of the mass changing. Anyway, so let's move on here. So there's another really big concept that we need to pin down in here, and it's called center of mass. So some of you guys, I think I've used the term center of mass in passing before with, you know, some sort of unjustified assumption that you have an understanding of what that means, but we should really define center of mass carefully. And so I'm going to start by defining it for a finite collection of masses, all right? So suppose we have M1, M2, all the way out through Mn at positions R1, R2, Rn, all right? So we have n masses that are at n positions, then big M will define to simply be the sum of the masses, M1 plus M2 plus Mn, right? Which of course we could write in a better way as the sum I equals 1 to n of M sub I, right? The total mass. That's the total, this is the total mass of the system. And big R, vector, is equal to 1 over the total mass, all right, times the summation I equals 1 to n of M sub I, R sub I, all right? This is the center of mass. The center of mass.
What's the difference between capital and lowercase r?
What's the difference between, I mean, they're not the same thing. I mean, I don't, what do you mean?
It's just the same letter.
Well, one's capital, and I'm not sure I understand your question yet. Say your question again.
What's the difference between using R vectors equal to R? Just the case difference. Using the letter.
Well, I'm using capital R for the center of mass. I'm using the little r's for the locations of the n masses we're considering. So if I was to draw a picture, right? If I was to draw a picture, we're talking about masses. I don't know where they are. They're out here or they're over here. You know. Here's the nth one. Okay. So here, I'm talking about, that's R1's position vector. Here's the R2 position vector. Over here, R3 position vector. Over to this guy, the nth position vector. I'm not sure where R is in my picture. Maybe. I mean, it really depends on how massive these different masses are, right? You know, for example, if M2 and M3 are ginormous, maybe this is where the center of mass position is. All right? I don't know, without, you know, further details. So this though, is the center of mass for the system. All right? I would say that this is a weighted average, but it's just not accurate, right? Would you like me to make it a weighted average? Behold. Now it's a weighted average. Tough crowd. Tough crowd. What's that? Otherwise, it's I don't know what I mean, it is technically a weighted average, but.
We're not finding the average. I thought we were finding the total mass, the summation of the mass.
Well, this is the weight. It really is the weighted average of the position vectors. And with the g there, those are literal weights. Is my point. This would be the weight of m1, the weight of the coefficient is the weight of m1, the weight of m2, the weight of mn, right? And this would be the total weight of the whole system, m times g, right? So it literally would be a weighted average, but we don't need to put the g in there because that's just obnoxious and really just for the purpose of a stupid joke, which may or may not have landed, depending on who you are. But yeah. But this is, yeah, I mean, you're right. It's the average. I would say it's the average position. In calculus, we sometimes talk about the centroid. You guys remember that? Centroid? No? Some not. Some people have seen it, some people haven't. What is centroid? Centroid is the geometric average of the points. So in other words, the centroid is what you'd get if you assume all of the masses have the same value. All right? So like, this becomes more manageable if we're talking two-dimensionally, right? So like here's simple enough example. If I put M1 here, and I put M2 over here, and if I put M3 here, right? And if I put M4 right here, you know? And these all have the same mass. What's the centroid? The origin, right? If I've drawn this wisely, you know? But if these really are all to the point, let's say, you know, vertices of a square, you know, the centroid would always be the origin, right? But if M2 is equal to 2m, M3, M1, is equal to 3m1, and M4 is equal to 4m1, if that was the case, right, then, and I mean, I guess I should tell you, like R1 is, I don't know, LL, R2 is minus LL, R3 is minus L minus L. R4 is L minus L for the sake of specificity, all right? If that's the case, if they're not equal masses, the centroid and the center of mass are not the same point. All right? What would the center of mass be now? R is equal to 1 over big M, right? Times M1 R1 plus M2 R2 plus M3 R3 plus M4 R4, by definition, a center of mass. Now, if I add these masses together, what's M1 plus M2 plus M3 plus M4 here with my made-up example? 1 plus 2 plus 3 plus 4 was 5 plus is 10. 10 M1, right? So I've got 1 over 10 M1, and then I've got, M1. My R1 was LL, and then plus 2M1. My R2 was minus LL, plus 3M1. My R3 was minus L minus L, and then 4M1, L minus L, right? The M1s, they be canceling, right? The M1s cancel. It wouldn't matter if M1 was 10 kilograms or 1,000 kilograms. The story remains the same here, right? Uh-oh. Oh, man. All right. And so what we have is 1/10 of, let's see here. So we got, I'm going to factor out the L. I've got 1 minus 2 minus 3 plus 4 times L, comma, 1 plus 2 minus 3 minus 4 times L, which works out to is that 0? That's 0. That's cool. And we got over there minus 4. So there you go. That would be the center of mass in this situation. Does that make sense? Yeah, I've got like 1 here. I've got 2 units of mass here. I've got 3 units of mass here, and I've got 4 units of mass here. So I've got 5 on both sides, right? So there's no net mass this way or that way. It's in the center, and it's down here rather than up there because there's much more mass down here, 7, as opposed to the 3 above the x-axis. So yeah. What does this all mean? This means that if these masses, right, were, if you wanted to think of it, you could think of all 4 of these masses collectively as a single mass at the center of mass. If we want to think about these, this is the particle model. We can think about a collection of masses as a single mass, this time apparently at minus 4L, so it's like down here somewhere, right? Big M down here. This collection of 4 masses is effectively the same as one big mass M at center of mass R. And for that reason, we're going to find it interesting to introduce the velocity of the center of mass, which is dr dt. That's the velocity of the center of mass. Like, there's no particle there, and yet we're going to find it is a profitable, indeed a wise proposition to think of it as if there's a particle there. I'll explain to you why next class. That will lead us to the concept of conservation of momentum, which is pretty neat. What's that? What's that?
1 over 10 is 9.
Did I forget the 1 over 10? Oh, man.
And then did we just plug?
Yeah, there's got to be a 10 here. Okay, so thank you.
Is that what we just said? M1.
Right here instead, right? My bad. So M is there. Let me give you guys back your tests. Let me turn this camera off here.